I've spent years troubleshooting networks. I've seen a lot of industrial Ethernet protocols. They all operate on the same principle, but one protocol completely throws out the rulebook. Today, I'm going to reveal the engineering secret behind EtherCAT's incredible speed and show you exactly what makes it fundamentally different from what you're used to. Hey everyone, Alana here. Today we're talking about EtherCAT's architecture and performance. I've done my homework on this protocol and I want to share what I've learned. Look, I've installed miles of Ethernet IP and PROFINET networks over the years, so I understand how standard industrial Ethernet works. Every device gets its own frame, processes it completely, then sends a response. It's the store and forward approach we're all familiar with. EtherCAT throws that model out the window. Instead of individual frames for each device, it uses what they call processing on the fly. One telegram travels through every device in sequence. Think of it like a freight train that never stops. As it passes each station, cargo gets loaded and unloaded while the train keeps rolling. Now here's the engineering part that caught my attention. This processing happens in dedicated hardware called an EtherCAT slave controller. It's not software-based like we're used to with TCP IP stacks. Each device introduces only nanoseconds of delay, which is significantly less than the millisecond delays I have measured while troubleshooting standard Ethernet networks with my scope. The documentation shows this approach allows one frame to carry data for hundreds or thousands of devices. When you've spent years pulling cable for star topologies like I have, this kind of efficiency gets your attention. Let me put some real numbers on this. In my experience with Ethernet IP, you're typically looking at 5 to 10 millisecond cycle times for standard applications. I've tuned systems down to maybe 5 milliseconds when pushed hard, but that's about the practical limit with TCP IP overhead. EtherCAT's documented performance is less than 100 microseconds. That's literally 100 times faster than typical Ethernet IP installations. Now, before you think marketing hype, the speed makes sense when you understand the architecture. They've eliminated the protocol stack overhead that I deal with every day. But here's what really impressed me as someone who's fought jitter issues for decades. EtherCAT's distributed clocks. Every device gets a hardware clock synchronized to sub-microsecond precision. I've spent countless hours troubleshooting motion systems where slight timing differences between axes cause coordination problems. This level of synchronization would solve issues I experience regularly. Imagine a scenario where a 20-axis packaging machine executes its move 200 microseconds late, causing the entire sequence to malfunction. With distributed clocks, all axes get their commands synchronized to the same hardware time base. EtherCAT devices have built-in switches. 2 RJ45 ports minimum. This means you can daisy-chain devices instead of home-running everything back to a central switch. I can't tell you how many times I've looked at a control cabinet with 48 Ethernet drops, all going back to a managed switch, thinking, there's got to be a better way. With EtherCAT, you can route your network to follow your machine layout. Need to go down a conveyor line hitting 20 I/O points. One cable, daisy-chained. Here's something that would have saved me headaches over the years. Automatic address assignment. How many times have you dealt with IP address conflicts or forgotten to document which device has which address? EtherCAT Master discovers and assigns addresses automatically during startup. From a troubleshooting perspective, this improvement is huge. No more hunting through drawings trying to figure out which device is 192.168.1.10. After decades of installing separate safety systems with dedicated relays and hardwired circuits, safety over EtherCAT also caught my attention. You can run safety-critical and standard control data on the same cable. The approach they use is called black channel. All the safety intelligence is on the end devices, not the network. As someone who's had to certify safety systems, this is brilliant. The network just transports the data. It doesn't need to be safety rated. The protocol is TÜV certified for SEL3 with multiple error detection layers, unique addresses, frame counters, watchdog timers, and CRC checksums. From an engineering standpoint, this redundancy makes sense. One failure mode shouldn't bring down your safety system. What really gets me excited is that you can implement advanced safety functions in software like Safe Limited Speed or Safe Operating Stop. Try doing that efficiently with traditional relay logic, and you'll end up with a cabinet full of safety relays and a wiring nightmare. Okay, this is all excellent stuff, but let's be honest about where each protocol fits in today's modern facilities. Ethernet IP is my go-to for discrete automation. It's everywhere, especially in North America. If you're working with Rockwell PLCs, the integration is seamless. Device selection is huge, and most plant IT groups understand standard Ethernet infrastructure. For typical factory automation with millisecond timing requirements, it works great. PROFINET RT performs similarly to Ethernet IP. Both run over TCP IP infrastructure. PROFINET IRT is different. It uses specialized managed switches to achieve sub-millisecond performance. In Siemens heavy plants, it's a natural fit, but those IRT switches aren't cheap. Here's how I think about it. Ethernet IP for standard discrete automation, PROFINET for Siemens ecosystems, and EtherCAT when you need the absolute fastest timing and tightest synchronization. Each has its place. If you're doing basic I/O with cycle times above 5 milliseconds, Ethernet IP is probably fine, and you'll have more device choices. But if you're synchronizing 10 plus axes or need sub-millisecond timing, that's where EtherCAT's architecture really pays off. Now let's discuss the economics, because that's a big factor when you're specifying a system. After installing dozens of networks, I can tell you that device cost is just part of the story. Infrastructure and installation labor often drive the total project cost. Here's the fundamental difference. Ethernet IP and PROFINET use star topologies. Every device connects back to a managed switch. EtherCAT uses a line topology. Devices daisy chain from one to the next. This topology difference drives most of the cost variance. A good 8 to 16 port industrial managed switch runs $500 to $1,500 depending on features. For a machine with 50 devices, you might need 3 to 6 switches, plus patch panels and rack space. I've installed enough of these to know the hardware costs add up fast. PROFINET IRT is even more expensive. Those time synchronization capable switches command premium pricing. You're looking at specialized hardware that costs significantly more than standard managed switches. EtherCAT eliminates switch costs entirely. The research I've done shows this creates a fundamental cost advantage that increases with system size. Small systems with under 10 devices, the costs are roughly comparable. But for medium to large systems with 40 to 100 plus devices, EtherCAT's savings become substantial. From an installation perspective, daisy chaining devices can cut cable installation time significantly. Instead of home running 20 individual cables to a switch, you're running one cable that hits devices in sequence. That's real labor savings. The research shows EtherCAT devices need ESC chips, but due to their high volume production, this cost impact is minimal. Meanwhile, automatic addressing eliminates IP planning and network configuration time. No spreadsheets tracking which device has which address. No subnet planning. So how should you think about the economics? Well, for simple, small systems, any protocol will work cost-wise. But as your device count grows or you need high-performance synchronization, EtherCAT's infrastructure savings become the deciding factor. You're comparing EtherCAT's device costs against PROFINET IRT's expensive specialized switches. EtherCAT wins that comparison. So what is the flip side? Ethernet IP has the broadest device ecosystem, which can mean more competitive pricing and more vendor options. Sometimes having 20 suppliers competing for your I/O business drives better deals than a smaller ecosystem. So here is my advice. Calculate your total installed cost, devices, infrastructure, installation time, and commissioning complexity. Don't just compare device prices. The protocol that looks more expensive on paper might save you thousands in installation and infrastructure costs. The applications where I see EtherCAT making sense are the ones where timing is absolutely critical. Applications such as multi-axis CNC machines, high-speed robotics, precision packaging, and the semiconductor industry necessitate that need for tight coordination between multiple moving parts. Now, based on my experience with high-speed industrial networks, cable quality would matter more with EtherCAT than standard protocols. When you're pushing data at these speeds, marginal connections that might work fine with Ethernet IP could cause intermittent problems. Always make sure to use good shielded Cat 6 or better, keep your grounds clean, and watch your bend radii. I've troubleshot enough network problems to know that most intermittent issues trace back to physical layer problems. EtherCAT also requires more understanding of real-time concepts. If your team is accustomed to using plug-and-play Ethernet IP installations, they will face a learning curve. The performance benefits come with increased complexity. So my take after researching this protocol thoroughly is that EtherCAT is impressive engineering that solves real problems in high-performance applications. The processing-on-the-fly architecture eliminates bottlenecks I've dealt with for years in standard Ethernet installations. But like any tool, it's not universal. If your application works fine with 5 to 10 millisecond cycle times and you need broad device availability, Ethernet IP is still a solid choice. If you're in a Siemens world, PROFINET makes sense. EtherCAT shines when you absolutely need microsecond level timing and tight synchronization. The question is, do you actually need that performance? Or would simpler protocols serve your application just as well? My final advice? Match your protocol choice to your actual requirements, not just what sounds impressive. Sometimes the highest performance option isn't the right engineering decision if it adds complexity you don't need. Well, that's my technical dive into EtherCAT. If this helped you understand how it differs from the protocols you're already familiar with, give it a thumbs up and subscribe for more practical automation content. Drop a comment and let me know what's driving your protocol selection decisions. Existing infrastructure, performance requirements, device availability. Your real-world experiences help everyone learn. Until next time, this is Alana reminding you, good engineering is about understanding your options and making informed decisions. See you in the next video.